there is another option that I need to discuss with you, that I need to talk about section code, then I need to back to here. But let's have a look at modal information a little bit. I can just deselect all of them just to make it a bit more clear for me. I'm just selecting modal information, and in modal information I have few options. One is the modal period and frequencies. The other one I need is modal participating mass ratios. That modal participating mass ratios show me which modes are my fundamental modes for earthquake design. So let's have a look at that. So I'm coming here because I added table, so still the other tables are here, but that's fine. So I'm coming here first to modal periods and frequencies. So mode 1 is 0.9596 seconds, and then 0.88 seconds, and coming down. Okay, but how can I figure out which one is my fundamental mode? It's not necessarily the highest period. We need to check the modal participating mass ratio. So if I come here to modal participating mass ratio, here I can see in X and Y direction which mode has the maximum participating mass ratio. So 62% of the mass is here. So that shows to me that this is the fundamental period for X direction. For Y direction, this one is the maximum mass. You can see the rest are very small. It's not necessarily the first and second one. It could be number 4 and number 10. Really back to the period you have. Sometimes you have some very soft elements in terms of stiffness. So you may have, for example, a cantilever here with period more than 1 second. And this cantilever is nothing. The modal participating mass ratio could be less than 1%, even 1.1%. But it's there because this is the highest mode. The order you see here is based on the highest period, but it's not necessarily the fundamental period. So you need to come here and have a look at that. If you are doing response spectrum, which is again for advanced course, I'm just giving you very basic information here. You need to come here to some X, Ux, and Uy and come to the end and see how much you could utilize the mass in this modal analysis based on the number of modes. Currently it's just 66 and 65%. This is not enough. You need to go over 90%. I personally always go more than 95%. So you need to add more modes, could be up to 200 modes, really back to the structure you have. So those are the tweaks you need to do, and when you find your fundamental modes, then you can check based on your local standards that if you can normalize earthquake to a certain percentage. In Australia, you can reduce the base shear of earthquake up to 70% of the calculation based on approximate method in the standard if the period of the fundamental mode is higher than the calculated period you have. And the other thing you need to consider is sometimes this period is less than what you calculated for a static analysis based on actually approximate method. It's really back to you if there is any provision in your standard or not. If they said no, if you know that the period is less, that means the structure is stiffer, then you need to use this modal analysis result for your calculation. You will end up with more base shear. In Australia, we don't have any clear provision about that. I personally try to be conservative all the time if it's not significant impact on the cost of construction. It really depends on the importance of a structure as well. Guys, those are just numbers. You need to make decision what is the safe and sustainable way and align with your code of ethics in engineering and use them. So this is basically what I wanted to share for modal. One more thing I need to say about mode. When you use a spring, actually you make the structure softer. So the modes are with higher period. So currently if I come here and check my modal response in mode 1, you see the first period is 0.95 seconds that we saw. So let's make it 3D. So you see this is in X direction. So if I start animation, you can see it's moving in this direction. If I go to the next mode by pressing here, currently this is mode 1. If I press here, I can automatically go to mode 2. So this is mode 2. And if I start animation, you see the structure is moving this way. So currently our modes are 0.95 seconds and 0.88 seconds. So let's see if we put the restraint for all joints below, what will happen, because you can see the paths are moving now. So that means you have more flexibility and ductility in the structure because of using a spring as a support. So I stop this one here and I save this file and then save as a different name. So for example, test. Then in the test model, what I will do, I'm coming to the base, which is my foundation. You can choose your base from ground floor because we discussed about that, but for modal analysis my recommendation is keep your support to the end. Don't remove your basements. Make it more accurate and reasonable in terms of behavior. So you can come to the basement level, to the foundation level, and select all those joints and make them pin support and apply. Doesn't matter whatever is below, piles, springs, or springs on the wall, it's okay. As far as you put the support here, is fine. So that is the foundation level, that is the base level of the structure. Okay, let's run it again. And see what would be the difference in period. It could be sometimes up to half, depends on the type of a structure and the flexibility and ductility of the superstructure. Because this structure is very short, I wouldn't be surprised if the first period is something about 0.5 seconds. So let's see what's coming up. Even here you can monitor it and see the result. Okay, the first period is 0.48, so it's shifted. This is the iteration because of the spring, so you can see some numbers coming here, some iterations happening, some shifting in the stiffness to make it work. Those because of the springs. The period after trial and error would be correct. So let's run finish and we will check the result together and see what's happening. So those are for P delta and earthquake calculations. Now we can go to the table. So let's have a look at the table here, show table and the structural output. If you come to the detail, modal participating mass ratio, you can see UX is not the fundamental period anymore because these numbers are very small. The second mode is for UX, just 49%, and the third mode is for UY, which is 57%. But if I come to the sum to the end, I can see here 58 and 58%. That means this is now less than before. So you need to add more modes to be able to get it really back to the behavior of a structure. I'm expecting to see more. So let's see what's happening in deform shape. That gives you a good indication to see what's happening here. So this is mode 2. So if I come here, mode 1, and apply, see what is mode 1. Mode 1 is not a major mode, is a torsional mode now. It's not translational mode. So if I press show animation, you can see it's a torsional mode. And if I go to the next mode, the next mode is translational in X direction, but the period is less than 0.4 seconds. So a structure suddenly become very stiff. I told you I wouldn't be surprised if the period is less than 0.5, is even less than 0.4. So a structure is very stiff now. And why the mass is less? Because part of mass, a big part of mass, which is ground floor, and the basement now is fixed. You don't see any movement. So that's why the modal participating mass ratio is less. So let's move on to the next mode. So mode 3, this is for y direction, and it's just 0.34 seconds. That means more stiffen a structure, more lateral load you need to apply to the structure. So this is less than half of what we had before. You can see the difference when you add a stiffness below. Why suddenly change? Because you have a massive retaining wall all around. So literally from ground level below is absolutely fixed. So it doesn't matter even you put your lateral support here at the ground floor or at the foundation level, because this box with the ground floor slab and retaining wall around and foundations below is very stiff, and actually a structure is vibrating from ground floor above, which is correct, which is what we expect. But when you had a spring around, it depends on the stiffness of the soil, it could be variable. It's really back to the sensitivity of the structure and the importance of the structure, that if you want to have a full model in modal analysis and response spectrum analysis, or you want to use it based on the base level of the earthquake. Okay, so this is what I wanted to share about tables and modal analysis. Now the only items remaining is section cut and draw elevations. So let's back to the plan on the form shape. Now, for example, I want to see this wall elevation. This wall is not on our grid, so if I activate the grid lines, you can see I don't define any grid line here. So how can I see this wall? I can go and select it in 3D, but if I want to see it properly in elevation, I can draw an elevation here. So what I need to do, I need to come here, there are develop elevation definitions, and then I can select this, and then it's automatically draw for me the elevation. So I can see the elevation here. I can name the elevation, for example, wall 1, and I can add it here and press OK. This is in my elevation from now on. So I can check, for example, whatever I want to see. If I come here in shells and I want to check, for example, F22 for earthquake load. So this is in Y direction, so I say earthquake Y, F22, and apply. So I can see the loads here and other internal forces if I want to check. So that's how you can draw different elevations. Then the other option is useful for you is section cut. So the load here on this wall is different in different areas. You have different axial internal forces. So how you can see the total axial force for this wall, you need to draw a section cut. For drawing a section cut and using section cuts, there are two options. One is a temporary section cut that you can draw anywhere. When you are in the deform shape mode, you cannot draw a section cut. When you use any internal force or stress, then you can come here again to draw a section cut and say, okay, I want to draw a section cut from here to here, and it gives me all information at this level. So here are all internal forces for moment and force in local 1, 2, 3, and also in Z. So you can see Z and 1 and 2, left and right side, and gives you the numbers. And here what do you have? It shows you that this section cut may cut other element, like for example frame element or solid element. All of them in the section cut will be added together, the numbers, internal forces, and coming here. How you can play with this? For example, here I want to move this cut a little bit up. Because this is axial load, you may not see much difference here, which is normal because loads are very uniform, but if there are other internal forces, you can see the difference. So if I come here, for example, change this one from Z2 to Z2, this line will be moved up. It may change, may not. Let's see what's happening. Yeah, it's not much change, but I move this Z. If I, for example, come here, change X, this is different. This is not this line. Actually, I'm moving this section cut in other locations in the building, and it may cut some more elements. So those definitely, when you change these, some of them will be changed. So if you have it, look at this number, when I refresh, you see these numbers change because now the section cut is cutting more element, but you cannot see them. What is visual is just the line here for this element that you can see. So it's good that you can find the total force in element and see what's going on. So if I close this one and go to other walls to see if we have any better view, for example, if I go to the retaining walls we have, so I'm putting the deform shape and coming here to XZ and moving to where we have retaining wall here. Then again I show, for example, F22, say for earthquake. Now you see different numbers here. I can have a long section cut for all of them, or I can have a partial section cut. It's up to me. I can come here again, draw a section cut. So this is temporary. You can save it. There is an option for save. So when I draw this one, I can save this cut. So if I come here and want to save it, it mentioned that add a section cut like this. So currently I have this section cut in my outputs. So currently these numbers are here. You can see the total Z, for example, axial load is 5,822 kilonewton. So if I play with this, for example, currently it's all the way. So I want to, for example, make it just very small. I can check the coordination, or I can play with these numbers to figure out. So it's from -1 to 33. I want to come to the last part. So if I, for example, put here from 31 to 33, this line would be just for this part, and these numbers would be very small. So if I refresh, you can see this 5,000 changed to 299 because I'm just addressing here. Now the Z hasn't been changed, so the slope you saw here, all of them consolidated to this short line. I can change this one to a certain elevation, so -2 and -2, and again refresh it. So this is a small one. I can choose exactly the area I want to see. I just need to know the coordination to be able to see that exact area. Sometimes you don't need to see the extreme fiber stress or force. You need to see the average of the force or stress in a certain area for example, to see the extent of your boundary elements. So that section cut is very useful to give you those numbers, because those are not something that you can find easily in the structural output. The other option we have for section cut is a permanent section cut. You can draw a section cut and save them, which is okay. So if you come to display and go to show table, here is an option for a structural output. If you open it up, you see other output items. This is what I told you that I will explain later. So you come here, you can see section cut forces analysis. If you keep this one and press OK, you can see the chosen section cut you have with the name you saved based on the load cases you already selected in the table menu before clicking OK. So if I press down and come here again in display, show table, and here change the load cases I want. For example, I want to see all envelopes for this wall, and press OK and OK here. I can see section cut for envelope U, envelope W, and envelope S, maximum and minimum numbers. But this is when you draw them one by one. The other option is define a group and assign a group of elements to a section cut group clearly. So that would be from the beginning, when we know we need information about internal force of a group of elements. So let's try this. If I get back to the wall we actually have here, we draw an elevation, we name it wall 1. To see that, we need to come to named view, and here we have wall 1, and I come back to this. So what I need to do, I need to select the wall and all joints around. Intentionally I'm not doing this, I'm just selecting shell element to show you what will happen. I need to come here to define and define a group. Here I need to add a new group, say wall section 1. I press OK, OK. Then I need to come to define section cut. I need to add a new section cut. I can name it the same, wall section 1. Here I have options, select by group, or this option. You need to give the coordination. Here we just using group. This is not for this course, and we just going for group. Here in group I need to select the name of the group I chose for these elements, and then here I can say I need section cut result based on analysis or based on design forces. And here I can say either the default, or I can mention exactly which coordination I need to see the report. For example, top part of the wall. Actually default is generally the base of the element. And then I select this one and I press OK and OK. Then if I get back to show table, I have this option active still, so it's showing me the section cuts, and I leave this one as it is currently, and then I'm coming here. You see the wall section, but everything is 0 because I didn't choose the joints. So if I get back to this and again select all the joints and just add it to the group, so I need to come to assign group, wall section 1, and apply, and then again back to this table, I can see the result now, but based on the load cases I chose. So if I want to change it, I need to come here to display again, show table, and for example I can select envelopes, press OK and OK, and here it gives me all loads based on the envelopes. Okay, so guys, this is what I wanted to share for result of analysis. I try to be a bit more visual in my courses and my training, because I believe just giving you some documents and tell you what is right is not the way to show you, because when you know the mistakes, it's way easier for you to avoid of this. So hopefully it was useful for you, and in the next series of video, which is for our last module, I will show you how to design elements and how to see the report of the design.